Okay, hello class. The other day we were looking at the sum and difference formulas. Today we're going to be extending that, and we'll be looking at double and half angle identities. The other day we looked at things like this, cosine A plus B. Today we're going to be looking at how that gives us formulas for stuff like cosine of 2A or cosine of A over 2. Let's look at the double angles first. So we're going to start off by just recalling that the sine A plus B is equal to this here. And instead, we're going to be thinking about, well, what is the sine of 2 alpha? We could just rewrite that as the sine of alpha plus alpha. And so we plug alpha into here. We plug alpha into beta as well. And then we get this. We have two like terms here, so we can then add those up, and we get the identity that sine of 2 alpha is 2 times sine alpha cosine alpha. Similarly, we do a similar kind of thing with the cosine, and here's the cosine identity. The sum of cosine of alpha plus beta is this. Instead, we're going to treat cosine 2 alpha as cosine alpha plus alpha and plug that into this. We get the following. That gives us cosine squared alpha minus sine squared alpha. And this is an identity right here, a good one to know. But we can also extend this if we consider that sine squared alpha itself can be thought of as 1 minus cosine squared alpha. Then we could turn all of this into an expression that just has cosine in it, cosine squared. So we have 2 cosine squared alpha minus 1. That's an alternative form, and we have an additional alternative form where we take this cosine squared and turn it into sine squared, where we think of it as sine squared alpha. And then that gives us 1 minus 2 squared, or 1 minus 2 sine squared alpha. So all three of these are equivalent forms of the double angle formula for cosine. Sometimes it's useful to have cosine in there only. Sometimes it's useful to express it as sine. Sometimes it's useful to express it in terms of both sine and cosine. So here are all the formulas right here. I didn't show the how we derive tangent of 2 alpha, but it's pretty straightforward from just the sum formula for the tangent. So here are some problems that I want us to just try out, and I'll give you a chance to do these. You can stop this video and restart in 3, 2, 1. So here are the answers to these. I just want to highlight the fact that I'm always drawing out these little diagrams here of where the angle is. In this case here, we have sine alpha is 4/5. That would lead us to either draw the angle here, where we have sine of 4/5, or over here, but we also have the restriction that cosine alpha must be negative, so that means the triangle must be over here. The angle must be on this side, because the x value must be negative. So that then means that this is our angle here, from here to here, and we have all the values in our triangle to figure out sine, cosine, or whatnot. So we have sine 2 alpha here, we extend it out, and then we plug in 4/5 for sine and negative 3/5 here for cosine. I'm not going to go into the details for these other ones. I just wanted to talk about how always draw out these triangles that relate the given information to the problem. Okay, I'll show this in 3, 2, 1. Okay, let's look at half angle identities. Again, we're going to start off with a way of expressing cosine 2 alpha. And what we want to do is use the sine version of it, so the 1 minus 2 sine squared alpha. That's what we just looked at. We're going to now solve for sine alpha. So what we're going to be doing here is we're going to be moving it to this side, moving cosine to the other side, and then we're going to be dividing both sides by 2, and then we're going to be taking the square root, not to forget the plus or minus sign. And this is something I'm going to come back and talk about. That plus minus sign actually should be kind of curious thing to put in front here because, if we talk about the sine of an angle, we've always only talked about it having one answer, so it's kind of strange to have a plus or minus in front of it. We'll talk about that in just 1 second. Let's do the same thing for cosine 2 alpha. For cosine alpha, but we're going to express cosine 2 alpha in terms of cosine. So this is from the identity that we just covered. In this case, again, we're going to be solving for cosine alpha. We divide both sides here by 2, take the square root, not to forget the plus or minus sign here again. So you notice that these two formulas are actually really, really similar. Only difference is this plus and minus sign here. Okay, let's go back and talk about this whole idea about this plus or minus sign. Or actually, here's the identities here. I just kind of captured them all. Our sine alpha over 2 is the same as 1 minus cosine alpha over 2, square root of that. But the plus or minus, we need to talk about that. What that really means is it's not both. What it means is we have to figure out which one to use. That sometimes we need to use the positive, we need to put a positive sign in front of this. Sometimes our answer must be negative. And it all really depends on what quadrant alpha over 2 is in, whether it's a sine or a cosine, whether we choose a positive or negative. It's all about, here's an example. So for cosine 100 over 2, that's equal to 50 degrees. That's in quadrant 1, so we need to have a positive sign in front of it, because cosine of 50 is positive. But in the case of cosine 200 over 2, that's cosine 100. 100 degrees is in quadrant 2. The cosine of that will be negative. So we need to put a negative sign. After we, calculate the inside part of it, take the square root, we choose, we're going to put a negative sign in front of it because we know the cosine of 100 degrees must be negative. Okay, so again, we'll just end this lesson with a few exercises. I'll show the answers in 3, 2, 1. I'll just comment real quickly on some of this. We can use the half angle here to say that 30 divided by 2, that gives us our 15. We know sine 30, that's why we chose 30 over 2. We know cosine 30, Cosine 30 we know is square root of 3 over 2, that's the exact value, and then we can then kind of do some simplification work to get it down to here. With cosine 7 pi over 12, we know cosine of 7 pi over 6. That's one of the special values in our unit circle. We know that that's the negative of square root of 3 over 2. And again, gets actually to a very similar answer to over here. I'll show the other answers in 3, 2, 1. A comment on these two again. Now, we notice here we put a negative sign in front of here because this angle 7 pi over 12 is actually an angle somewhere like right around here in the second quadrant. So we know it must have a negative value for its cosine. This value over here, if we draw out this point -3, -4, we know that it gives us this angle here. Half of that angle is going to be somewhere over here. So we know the sine is going to be positive for the half angle. That's why over here we chose the positive version. Okay, last one here. Here's a little hint before I show this. Try to work down on the left-hand side and make it the same as this. Okay, so here's the answer. We use the half-angle identity to bring this down here. Now the magic is this. I want to match the denominator over here. And I have that inside here, but I have the square root of it. So I'm going to multiply it by the square root of 1 plus cosine alpha over 1 plus cosine alpha. I'm multiplying by 1, so it's a safe thing to do. And so now I have my 1 plus cosine alpha, quantity squared down here. So when I take the square root of it, it becomes the denominator that I want. Now, up here in the numerator, I have a minus b, a plus b type of structure. That's my difference of perfect squares. So 1 squared minus cosine squared. And that's just merely sine squared alpha. Take the square root of it. I get sine alpha as I wanted. Okay, have a good day.